Hey guys, this is a first class lever here. Let me just bend this camera down a little bit. So this is a first class lever. Here's my whole machine, but you don't need to see the bottom part. You just care about this part on top. That is the lever, okay? So if we look right here, this is a first class lever. I asked you if you could kind of have it so that it's not right directly in the middle. If we have it directly in the middle, then one side's the same length as the other side, and the mechanical advantage is 1, which is not really much of a mechanical advantage at all. That means that if this weighs 100 pounds, you would have to push 100 pounds to lift it, and there's really no advantage at all. So I asked you if you could kind of offset it a little bit, please, so that one side is longer than the other. And This is a first class lever, and there's a weight on this side, and this is the side you push to lift it. So I push down, and it lifts this big heavy weight. Um, we're going to pretty much look at two things: the distance of the resistance right here and the distance of the effort, and those are always measured from this point right here where the shaft is, where it kind of tilts and rotates from. That's called the fulcrum. The fulcrum looks like that triangle. So if you see that triangle, that's the fulcrum. That's where it's kind of balancing from. It could be at the end, and it could be in the middle, or somewhere anywhere in between. So as you can see, we can kind of just move this fulcrum wherever I want. I pull it out and put it somewhere else. And we're going to use a ruler to measure it. I would probably use this top centimeter part right here. The reason being is it's harder to read these, and these are really easy. There's 4, 5, and there's even middle points like 5.5 and so on and so forth, and it's in decimal. So just use the centimeters is fine with me. You can do that in this particular activity. All right, so enough with this video. Sorry, before I actually cut this video off, let's just show you one more thing. This is your first class lever. That's because the resistance is on the opposite side of the fulcrum as the effort. So the effort and the resistance are on opposite sides of the fulcrum, that little triangle thing. If we do second class lever, we have to move the fulcrum to the end, and we put a weight somewhere, anywhere here. It doesn't matter. It could be here, it could be here, it could be here. And our effort is at the end. So I put my finger and I lift it up here. So now this is the distance of my resistance from here to here. And the distance of my effort is from where my finger is pushing all the way to the fulcrum. So that's my effort, and that's my resistance. Third class lever, do not rebuild anything. You're totally good to go. This is a third class lever too, but I just have to move this around. The weight's going to go at the end, and my finger's going to go in the middle, kind of trade places. This is a third class lever. This is my distance of effort, still where my finger is, from here to where my finger is, but my distance of resistance is also where the fulcrum to where the resistance is. So it's the same thing, they're just in different spots. And in this case, the resistance, the weight, is always way further than your finger. So this number will be bigger. And this always gives a mechanical advantage less than 1. In other words, you always have to push harder than the weight. And that's pretty much it. The only thing I'd like to add is I added earlier in Zoom is that what is the advantage of this? So I put this, I'm going back to first class lever. What's the advantage of this? So I lift this weight up, and I get to push it down and lift that weight up, but I get to push less hard. But the disadvantage is I have to do it further distance. So I move from here to here, like all that distance there, but my weight only moves like that far. So you have to move further, and the weight's not moving that far anymore. So that's the disadvantage, but the advantage is you push less hard. So that's kind of cool. And that's enough. Now let's look at the math of it real quick. All right, folks. So here we go. Looking at a first class lever. In fact, I'm going to write the equation right here. IMA, sorry for my handwriting here, is equal to distance of effort divided by distance of resistance. And what is IMA? IMA is ideal mechanical advantage. And what does it mean? So if you have, let's say, for example, let's say IMA is equal to 4. Let's say if your IMA is equal to 4, and you have this first class lever, and you have a little fulcrum right here, and we put a weight right here. What that means is that if this weight is pulling down and resisting you with a weight of, let's say, 40 pounds, that an IMA of 4 means you have to push 4 times less. So that means you have to lift that up. You push down with an effort, and this would be the resistance, by the way. The resistance, the effort force, and technically we should probably put force of the resistance. The force of the effort would only be 10 pounds. That's all this means, okay? We'll worry about that later. We're not really doing AMA right now, which is actual mechanical advantages with weights and stuff. We're just doing what the ideal mechanical advantage of your machine should be. So, looking at this, that's all that means. So the bigger this number, the easier it is to lift something heavy. So like I said, once again, if you have an ideal mechanical advantage of 4, then whatever weight you're lifting, it's 4 times less to push it. So you would only have to push 10 pounds to lift it, which is kind of cool, right? All right, that being said, let's get out the old eraser. There's an eraser in here somewhere. There we go, soft eraser. Wait, can I just get a regular eraser? Is there not like a hard eraser? Oh, there it is, I saw it. Hard, forgive me, I'm new at this. Hard eraser, and let's just go with the big size, full ink flow, and oh, I don't want to do that. Control Z. Let's hopefully you wrote this down. You could always pause the videos and rewind these things and stuff, so in case you want to hear me say that over again. Now, going back to this, a first class lever, a first class lever looks like this. It has a lever, and it has a fulcrum somewhere, and then it has to have a weight, and then it has to have an effort, you know? So let's just say this is your effort. And the distance from the fulcrum, this is the little balancing point, that would be your shaft on your lever. This distance is what we call the distance of the effort, dE. And this distance right here, the distance from the fulcrum to the weight, would be the distance of the resistance. And distance, like measured in centimeters or inches, it doesn't matter. We divide them and they cancel out anyway. So I think I told you to use centimeters. It just works out a little bit better. And then we just divide them, and simple as that. For example, if I were to measure this one to be 5.5 centimeters, and I think I did that in the first period class, I actually measured mine. And let's say that it was 5.5 centimeters away, and over here it was 13 centimeters away, right? So if I found those two answers, go ahead and you would write those in your notebook, and then if you want to calculate the IMA of this machine, you would just say the distance of the effort is 13 centimeters, and the distance of the resistance is 5.5 centimeters, and then we just divide them and find out what it equals. This is not a nice even number, so I'm going to go ahead and click search, and I'm going to type in calculator, and then just type in 13 divided by 5.5 is equal to 2.36. So let's get back to the magic over here, 2.36. 2.36, and that's my answer. Okay, so I just found the IMA of this machine. All I had to do is measure the distance from the fulcrum right here to like the end of the thing. Technically in class we'll measure to the middle of the weight, but for now I just said to make things easy, just measure from the fulcrum to the end, and then from the fulcrum to the end over here. And then get those two numbers, and that would be the ideal mechanical advantage of your machine right about here. 2.36. What does that mean? It means that it would be 2.36 times easier to lift the object, like weight-wise, you know? You would have to push 2.36 times less. Okay? And that's all that means. So here's how you do your first class lever. The second class lever, let's do that one now. So let's go back to the hard eraser, and let's do the second class lever. And I'm using the same equation again. So here we go, second class lever. And for that we need a lever, and we need a fulcrum. But the fulcrum's going to be at the end. It doesn't matter which end. I could draw it on the left or the right. So there's my fulcrum. And you need a weight. And the weight is going to be somewhere in the middle. It could be here, it could be here. It doesn't matter where you place it. I'm just going to kind of put it right there in the middle. And it's going to push down here, okay? And then you need to push up to lift it, of course, this direction. And this would be the force of your effort. and that would be the force of the resistance. I don't need to know those numbers right now because we're not calculating FRs and FEs, we're doing DEs and DRs. So you will need to calculate, you'll need to measure, I should say, from the fulcrum to here, and remember that's your resistance, so this is the distance of your resistance. And then your effort, you're going to have to measure from here all the way to the fulcrum again, and that will be the distance of your effort. Let's say that this was 20 centimeters all the way to the end, and this one was, I don't know, let's say it's 10 centimeters. It looks like it's about halfway, right? So let's say that's 10 centimeters. So if I want to calculate the IMA, it's going to be DE, 20 centimeters, divided by dr, 10 centimeters, the dr here, and 20 divided by 10 is 2, and of course again the centimeters just kind of cancel out, and the answer is 2. There's no unit here, so that's the funny thing about this. There is no unit. You're probably used to science going, oh, it's every answer is in inches or meters per second or you know, feet or whatever, but no, this is just 2. It's like a ratio. So what it means is 2, that here you have to push up 2 times less than here. That's all that means. The number's big, and the bigger the number, the easier it is to lift. So if you get an answer of 1, that means it's the same. Like if it's 5 pounds, you got to push 5 pounds. If it's 10 pounds, you got to push 10 pounds. That's what 1 means. 2 means you're pushing less now. So 2 times less, so you'd have to divide by 2, but 2 times less. So in other words, instead of lifting 20 pounds, now you only have to push 10 pounds to lift a 20-pound object. I want you to note though that in this case, a second-class lever right here. If you're doing a second-class lever, you will always have an IMA greater than 1. You will always have an IMA greater than 1. So it'll always be easier to lift. That's because if you're doing it right, if you're doing a real true second-class lever, you're always going to lift out here, which is further away than the weight. Because remember, you have to put the weight anywhere here, anywhere, and then you have to push at the end. So that means that this distance right here, this one, will always be bigger than this one, which means you'll always get a greater value than 1, which means it'll always be easier to lift. Okay? So that's a good little note to know. And you should probably write that down. But you can always pause and rewind these videos, remember. Let's go back to the hard eraser, and we're going to do the last one, and then we're all done. I just moved all my stuff around. I'll figure that out here. Oh, look, it moved back for me. I just messed up my DR up there. I'll fix that. So now I'm going to get lazy and just change that number. Let's see here. So this is DR. And now we're doing third-class lever. And the third-class lever looks very same as the second. In fact, if you're physically building it, they're pretty much the same physically. Your fulcrum's at the end, you have a lever. The only difference is you put the weight at the end, and you'll have this force that's pushing down that we'll call force of the resistance. And then to lift it, you'll have to push up somewhere in the middle, somewhere here, it doesn't matter. And by doing this, you've just created a third-class lever. It's just all you're doing is switching. Instead of pushing at the end and putting the weight here, you just switch those. And then now you have a third-class lever. And this would be your force of your effort. But remember, we don't need forces, we need distances, right? Look up here, we need distances. So I need to know the distance of, what is that? That's my effort. So I need to know the distance of my effort. How far away is my effort from the fulcrum? Then I need to know the distance of my resistance. How far away is my weight compared to the fulcrum? And like I said, you could just go to the end. This one you'll have to kind of make up. You're going to have to say, I'm going to put my finger here or something like that. And once you know where your weight is and where you're going to put your finger, you can take the measurements. And then I'll just make these up right here. So this one I'm going to go 10 centimeters. And I'm going to do 20. So it's pretty much the same as last time. And then, but the answer will not be the same. And because remember, my DR is now way out here. My FE is over here. Remember, I switched those two to make a third-class lever. So DE is 10 centimeters, and DR is 20 centimeters, and I get 0.5. When you start getting less than 1, remember the centimeters cancel out, so there's no unit here, it's just 0.5. If you're less than 1, it's harder to lift the weight. That means if this weight right here, if this weight weighed 10 pounds, you got to push 20 to lift it. Why would you ever want to do that? That's like dumb, right? Well, there's certain reasons why. Sometimes you want to make a machine that you move a little bit and the weight moves a lot, and then you just go, hey, I got to push harder, but it's cool because look, I just move a little bit and that the weight moves a lot. The other reason B is you might be making a workout equipment, and in workout equipment, um, using more metal makes things heavier, but it also costs more. So if I want somebody to lift 100 pounds with their little workout machine and it has a cable or a little lever that they're pushing and it's got a lever system that they're pushing, I can make them lift 100 pounds like this, but I only have to put a 50 pounds worth of metal over there. And if I make the lever right, I can make it where they feel like they're lifting 100 pounds, but really they're physically only moving 50. It would be weird because you would push like this far, however far this is from your arms, but it would move twice as far, like up and down a rack or something, like with cables or something. So that's why there's reasons why you would want to do that. Most of the time you wouldn't, because you're like, why would I want to push harder than the actual weight? I'll just lift the dumb thing up. It's easier. But there are times where you want to make a machine that does. It's harder to push than the actual weight of itself. So there is sometimes you want to do that. And I hope this makes sense. And all you have to do is take a picture of your work and put it on Google Classroom, and we're all good. Don't forget to email me, share, like, and subscribe. Be sure to hit that like button. Just kidding. I'm trying to sound like a YouTuber. All right, guys. Have a good one. Bye.